additive approximation piece for low dimensional embeddings. And this is with Ainesh grad student at MIT, Sherali-Adams, and Sam Hopkins, who's a professor at MIT. All right. But before I tell you about this problem and our techniques in particular, I want to set the stage with some background and context about metric embeddings. So, what's the general idea in metric embedding? Start off as your input, which is a set of parametric distances. Let them be represented by Vij for each pair of ij. And the goal is to take these set of distances and embed them in low dimensional space. So I'm using the notation of ik, think of k as small. And the output embedding is just some points in ik, represented by the x size. Okay, so what is the goal in metric embeddings typically? And the possible goal in metric embeddings is to minimize violations distortion. So what does that mean? You want to minimize L is a scalar, such that the distances in the target embedding are sandwiched between the input distances up to a factor. Okay. So what are some well-known examples of violations embeddings? The most well-known one is Johnson-Lynch stress. So let's say the input is your input been equated. And if it is, then it suffices to embed it in log n over epsilon squared dimensions. So p is log n over epsilon squared, and L is 1 plus epsilon. So you get a distortion of 1 plus epsilon as long as you embed it in log n over epsilon squared. Okay. Let's take this one step further. There's this wonderful result by Bourdieu who says that the Vij's are arbitrary metrics, so no longer Euclidean, arbitrary. We can embed them in n-dimensional space with distortion log n. Now, and if you combine both of these results, you can do Bourdieu first and then apply GL. It tells you that you can embed in log n or epsilon squared dimensions with distortion log n. Okay, for any inputs. Okay. But what if I care about embedding in really low dimensions? Like I don't want to pay log n, the dimension that I'm embedding in. I want to embed it in 1, 2, 3 dimensions so I can actually see what. Okay, so what is known about this? Let's try something natural. Let's use the Johnson-Lynch stress approach again. And one way to do this is to first embed it in the Euclidean space. And then take a random projection of the points in Euclidean space into k-dimensional space. Think of k as CV2 for now. Okay, so how do you do this? You construct the embedding by Bourdieu, then you multiply it by a Gaussian matrix where the Gaussian has k rows and n rows. Okay, so this will give you a set of vectors in space. Now you can ask, how well does this random projection embedding? Well, it turns out that this random projection embedding shows that the distortion that you get by left scales as n to 1 over k. Okay, so you root n of k. And the results are pretty compelling hard data that says you can't really do better than this. Like anything hard to approximate up to any factor better than 10 to the 1. So if you look at this, maybe an pessimistic outlook that you might have is that there's nothing really left to do here, right? Low dimensional embeddings are hard to compute. If you do a random projection, it basically matches the NPR nest. So let's just go home. But the story doesn't really end there. In fact, computing low dimensional embeddings is ubiquitous in practice. People do this all the time, every day for applications ranging from scientific computing to data visualization, graph drawing, and even training neural networks. So what do? They run algorithms like principal component analysis, or there's other class algorithms called BSNE, or multi-dimensional scaling. And these algorithms actually work on real world data. So here I took two Gaussians in the 100-dimensional space. And I ran these algorithms on it, like general Python packages. And as you can see, they recover these clustering structures. But if you do random projections, the algorithm I described in the previous slide, we get basically nothing. You just think that there's like one giant mess. Okay. So then the actual question to ask here is like, how do you reconcile this gap between theory and practice? So let me give you a more optimistic outlook on what is going on. And this is perhaps a controversial thing. But an optimistic outlook here is that the short is actually a yardstick to measure the performance of low-dimensional metric embedding. Okay, because essentially it's saying that there's nothing better that you can do than just better than you. But this doesn't seem to match outcomes. Okay, so what should we do instead? Well, this is what people do in practice. What they do is they write down an objective. And the objective function tries to capture the following. It says that the embedded distances should be approximately equal to some objective function that captures this. And there are several families of objective functions that behave this way. This includes PCA, like principal component analysis, PC, and dimensional scaling, which actually do. Okay, so you wrote down an objective function. Now what? Well, now we just run an algorithm that optimizes this. Okay, so what is the status of this new paradigm? Well, it turns out that there are literally no rigorous guarantees in the worst case for analyzing embeddings. But it's been pretty well studied in the statistics community, the data sciences. Any questions so far? There's a guarantee of PSNE that I'm not in the worst case, right? I am the worst. Yeah. Okay, so while this is happening in the record embedding literature, there is an interesting phenomenon going on alongside for optimizing using convex hierarchies. So what are convex hierarchies? Well, they're a powerful and general toolkit for solving optimization problems. And they unify several existing algorithms under one umbrella. So like you can capture max cut, sparses cut, max CSPs, even algorithms for unique games under one umbrella using these convex hierarchies. And there's been a lot of algorithmic breakthroughs using these hierarchies, but these breakthroughs are a little bit of average case problems. So these breakthroughs include results in robust environment statistics, community connection, but these are all average case problems. And if you look at this literature, maybe you can condense it in the following view. If you're stuck at designing an efficient algorithm, try using one of these hierarchies. Okay, but this comes with a caveat. And the caveat is that improving algorithms for worst case optimization problems remains sparse. There are exceptions, but not enough. Okay. So what is the overarching philosophy of this work that I want to convey? In one line, the philosophy would be convex hierarchies are the right toolkit for optimizing lower dimensional embedding types. Okay. And if you don't like one line, here is the philosophy of mean. You take this toolkit and apply it to lower dimension. Okay, so this is a fairly bold claim. What evidence do I have to justify? The evidence is the following. So we managed to use these hierarchies to get new approximation algorithms for essentially all the problems, right? Those for multi-dimensional scaling. There's other problem called Euclidean Metric Violation. And also entry-wise learning. So this is just the beginning, but I think there is like a growing sense, at least for me and my co-authors, that this might be the right toolkit to push such low dimensional embedding. Okay, so enough pontificating. Let me tell you what the top plan is. I'm going to start off by explaining what this Euclidean metric violation problem is. Now, I'll tell you why it's an interesting problem and what is told about it. Then we'll see how to solve it using these programming hierarchies. Then I'll end with some more quantification on where we're headed. Okay. So what is this low dimensional Euclidean metric problem? We're represented using A and the input, think of it as just a vector in n squared dimensional space. If you really want to represent, like, you should think of this vector as representing dissimilarities or like pair distances. And the other parameter in the input is k, which is the variable. So you want to take their distances and you want to embed them in k dimensional space. But what we really want is that the embedded should be the closest k dimensional Euclidean embedding to the set of input distances. And here I'm not even assuming that the input distances satisfy triangle. They're just some non-negative vector in this square. Now, you can write this in the philosophy that I mentioned earlier as the following optimization. So what is the optimization? It's just minimizing over all k-dimensional embeddings X. So here I'm representing the embedding as the very distances. It's a large representation in sort of space. And I want to minimize the L2 squared distance between the input vector and the embedding vector X. Now I'm going to represent this as options. Okay. Here's like a better way to think about the state of dynamism. And I'll switch between the two. There it is. Right. So I'm minimizing over points x1 to xn in RNK such that the distance in input space minus the distance in the Euclidean space, the p-dimensional Euclidean space. The difference square of these differences are constant. Any yes. So think of the vector D as an arbitrary vector coordinate. So you start off with some space. You know you put it as the one of the words you think that comes out of and embedding a total number. No, so I haven't. This is like let's say I want the distance to be equal to be equal to the distance of point there. Any other methods? Yeah, feel free to interrupt me. Okay, so let's do some fun examples using the subjective and see that as the trivial. Let's say D is the driver distances between 20-dimensional Gaussians. The first Gaussian has mean at minus B1, like some standard basis method. So their means are right there. So the comparison set. Now, if you solve this method, you get this nice picture that I told you earlier. It manages to actually recover the questions. Okay, let's do another instructive example that will highlight the differences between this particular objective and the other objective that you might be familiar with. So now let's say the input is just a grid metric. It's like this 2D metric. The input is every pairwise distance between the points of this. So what? Oh, can I ask it? Yeah. So what do you talk about random projection? Yeah. First thing that I can do would be project in like a cake of single vectors of the distance space. So that actually doesn't work. Like you don't have any triggers directly squared. I'll show it to you in action. I'll show you what happened in this step. This is like perfectly illustrating what happened. Okay, so we have this grid metric. And if you read this Euclidean metric violation algorithm on this, what you recover is like this cluster structure that still tries to preserve parameter distances between points along the y-axis. It doesn't collapse them. If you run an algorithm like PCA, where you just project onto the top eigenvector, it will actually, it's like it's just fixed the maximum variance directions. It will actually sit and collapse them the same. So that's why it probably should be. Yeah, great question. Any other questions? Okay, so let me now tell you what is known about this particular problem. And I'll focus only on Euler series. And in this really interesting paper from Dhamdhere in 2004, he shows that when the output dimension, the target dimension is once when you're embedding one to the client, you can get a log n approximation. Dhamdhere also attributes NP-hardness of this problem to this old paper of Sachs with 1710. Says this problem is NP-hard with my case. If you actually track down this reference, Sachs doesn't prove NP-hardness for this problem. In fact, is anti-hardness proof does not apply to this problem. It's an interesting historical anecdote, this one. But actually, there was this other paper by Dayton and Dasgupta from 2006 that does show anti-hardness, or exactly. Okay. And there is no algorithm guarantee for if I want to say even the plane. Whenever the target dimension is larger than 1, we have no rigorous guarantee. And this is also posed as a open question by Dhamdhere himself, and he said like there is no evidence for APX hardness for this problem, so it is entirely conceivable that there might be a and since people are interested in studying these metric embedding objectives more recently coming from practice, this problem was reiterated by Lee last year. Listen, what you're okay, so what is our result? Our result says that if you have this Euclidean metric violation problem, so you have your equation, and each of these distances can be represented by d bits. And you also given the target dimension and an accuracy parameter epsilon. There exists an algorithm that does the following. It's an additive approximation. It will output the k-dimensional Euclidean x hat with the following guarantee. If I look at the L smart distance between p and the then this is f1 off plus epsilon times the L norm function of over. Okay. So this is an additive approximation scheme. Why does this additive approximation make sense? Well, I can always output the zero vector x hat, right? In which case, I know that I'll incur a cost that has most L norm function. Okay. So here I'm doing better. I'm doing like x epsilon times the max. That's usually how we represent that. So these are vectors. Yeah, I'm not thinking as a vector and squares. So obviously, how you get x hat and vectors. What we're giving is something stronger. We'll give you the actual effect. It's just a convenient. Okay. We'll give you the good question. Other questions? Okay, so what is the running time of this algorithm? This algorithm runs in polynomial in n times, so add to a fixed constant. And it depends on the bit complexity is also called, but it depends on these input parameters scale. So it's e to the following theorems.
Do you use the fact that D satisfies triangle?
We don't. D is arbitrary non-negative. Arbitrary non-negative. And it's not clear that the input metric satisfying triangle inequality place.
But like a very weird D is also embeddable.
Yeah. Yeah. Nice.
From like if you're getting an epsilon approximation anyway, that you replace E with into epsilon and the error is supposed to find or there's something very sensitive like when you got if B is huge then epsilon you got E.
Well, if B is huge, you need to spend time working on the B.
But you don't have to
Yeah, it could be possible that you won't need to n times B and then some 2 to the poly. That's it.
What is your take role?
Yeah, that's right. Excellent question. Now there's like some sort of phenomena happening here that once D reaches like log n, you should expect to solve it. But any less than that, it seems like it's sorry. That the same phenomenon kind of happens when you analyze random variables. At log n, it's easy, but then you don't wait.
There. Wow, okay, so
You're completely correct, and I don't have a good explanation for this. The only explanation I have is why this study course is that when I tell you the outcome, you have to do more stuff if you're like 10 dimensions as yeah, I'll tell you why this is appearing in our analysis, but you know.
Epsilon doesn't get smaller.
Yeah. Anyway, so I'm still confused. What's the example that proves there's a large gap between K and the dot and vector thing? What's example that shows that this will do much better?
Yeah.
Than the argument complaint. It's like this great example where you collapse all these cases, so non-trivialized. Other questions? Okay, so some remarks about this result. It's to the best of our knowledge, the first polynomial time added approximately 16 for this problem. And we think it's like the crucial first step with obtaining a PTAS. So we don't really know how to obtain a PTAS, and we don't really resolve Dhamdhere's problem, but we make some progress on it. Another remark is that this, and this is a bit of a technical remark, this doesn't really require the full power of relaxations. You can get it very much stronger than this. Very things.
I think sorry.
One more question.
Yeah, when you follow us. Yeah. Your example illustrates that PCA is bad, but it doesn't say that opting here is much better. For all I know, opting here is also large, so yeah, you're able to approximate opting, but opting is as much as like the error of PCA, then it will get better.
Yeah, so you can formalize this a bit more and show that opti here will be like non like worst case is just like all these things are constant, like that's constant. So you can show here that like I think exactly that opti smaller than. Yeah, there's a way to get this precise, right?
So is relative approximation completely different?
Like a constant approximation.
What that's not basically.
Completely different. It's a stronger guarantee, and that's the PTAS. And
No, it's not clear. Well, yeah, but and so not be hard for say constant many dimensions in the most negative version.
no, so that's what this paper of Dhamdhere done for its conjecture. It's conjecturing that it is possible to get plus. And we don't know how to do this. Yeah, but we do get it. Yeah, it's also open to get a constant, just to get like both one.
I mean, what dimensions is it interesting? It's 1, 2,
1, 2, 3, in all cases.
and then they become roughly equivalent to each other or not?
Once the dimensions start scaling with the input size, you can do things like that. Like once you get the log n dimensions, the problem gets. Other questions? Okay, so let me tell you about our techniques and how we make progress in this problem. And if you get bored, so now the TLDR for our techniques is the following. We present a new analysis of global correlation modeling, which is tailored to these low-dimensional events. Okay. So we show that actually this whole technique of global correlation rounding does a lot better if you're analyzing low-dimensional events. Okay, so let's make some of this more precise. I'm going to focus on just embedding into 1D. And the first thing I will try to do is to formulate this optimization problem as a constraint satisfaction. Okay. So how would we do that? Well, this is a problem over unbounded domain. So a natural thing to try to do is to discriminate. Okay. So our area distances have a complexity too. How would you discriminate it? Well, here's an operator. Numbers are represented by base. Either the distances are 0 or they're between 1 and 2. That's the amount. That's how large numbers I can represent them. Okay, so here's a claim. What if you believe this discrimination? Here's a claim. So it says there exists an approximate solution. So there exists a solution given by these xi's, where the xi's take values in a discrete bounded set. So they take values that are either epsilon or 2 epsilon, and so on, all the way to just discrete distances. And they have the following guarantee. If I look at the embedding given by these xi's, the optimal such embedding, it will have cost which is proportional to opt plus, well, it's upper bound by exactly opt plus epsilon times this L2 norm of the distances. Okay, so now just took the L2 norm of the distances and wrote it as this. Okay, so recall that this is the amount of additive error that I was obtaining with. And this says we can take a problem, disguise it, and get the same amount of additive. Okay. So what is the upshot? The upshot is you can now try to write the constraint satisfaction problem what you're trying to recover is space as fast as possible. Okay. Good. All right. So I hope it will tell you exactly what the CSP is. But let me tell you informally what the CSP is doing. It's saying parameterize over gate-dimensional vectors. Or we're just like numbers because we're writing on the line. Where each number just takes one of these values. So x1, x1, and you realize this objective, which is the difference between the DIJs and the So now at least we have a CSP. And the second observation is that this CSP is dense. So the CSP has a constraint for every bare xi action. Okay. So what I can try to do is I can use some generic CSP, dense CSP software to get additive parodies. And this actually works. So if you run this generic CSV solver, you get an algorithm that runs in time with all that. And not only exponential in the bit license. So it's like exponential and 2 I'll tell you why it's not times it's supposed to follow zero. But it does get the right additive approximations. Get additive epsilon times the help. And I'm using okay, good. And there's this paper by Dayton and al. that actually implements this sort of strategy, but not for this objective. They were for a slightly different. Questions about densities, please.
So is this any kind of AKK algorithm, for example, or algorithm?
What is that?
That's the first algorithm for the CSP.
I'm not sure what their run is, but
This is the threshold right thing, right?
yeah. Also, the greedy algorithms also proteins. You know these greedy algorithms that do like regularity level based on yes, where you guess a subset and then you greedy yes, nils proteins. These are all equal. Yeah.
The poly K is still says like poly K. If you just utilize it's like vectors, like that's one that.
That's right. Okay. So let me give you a quick overview of how to solve dense CSPs using correlation. And then the stories will come up and then I'll tell you how to do it. Okay, so give this really nice word by Barack Obama for starter. They present this whole correlation around the framework for rounding, Sherali-Adams and some sorts of relaxations of mass CSPs. I don't really have time to explain what these things are, but for now, suffice for you to think of this as outputting a distribution over solutions. It's not quite a distribution, it's going to match low degree moments of the distribution, but for the purposes of this talk, the distinction is sort of irrelevant. You can't sample from this distribution, but you can do both. So what does this correlation rounding thing say? It says the following. It says that if I iteratively condition on the values of the variables, this produces an approximately pairwise independent distribution. Okay. So conditioning makes you more product. And the second thing is that if you are approximately pairwise, then you're easy to round because I can just round each variable independently. If you were truly product, this would be perfect. Okay. So if you combine these two things, it's saying either you can round really well, so you have a pairwise distribution, or you can make it more pairwise by conditioning on the value of two variables. Okay. That's the English version of what this table does. Here's the math. Okay, so here comes the distribution. Let me assume the distribution over x1 to xn because you're nice. And these x1 to xn take values in a discrete set S. Okay. Then if I condition on a subset of size, so capital T is a subset of size T. I'm drawing the values that I condition on from the right one. And this condition is super distribution or distribution. Satisfies the following. It says that on average over the choice of the set that I condition on, and on average over the pairs, The dp distance between the joint distribution and the product distribution is small as a function of c. So as I condition more, I take my original distribution, then I move toward the product distribution. Okay. So it's capturing what I said on the. The details of this are not that important. It's just this consequence that no one don't do. And now let me tell you what our algorithm is. Our algorithm is really simple. All it does is it computes the pseudo distribution that minimizes the objective. Then it conditions on d points the way that I showed you earlier. We'll just sample d points from the marginal. And after you've conditioned your pseudo distribution, just do infinite rotation. So route each variable to its product function. Any questions about the algorithm? I know I'm rushing. Okay. So how do you analyze this? Let me use the notation U prime tensor to denote the product distribution on each of the poles. And then let's say I use the notation yi to be the resulting sum from the product distribution that I wrote. I want to analyze this cost. I want to analyze the cost, average over the layers of the embedding minus distances squared. So I'm going to use a basic trick here where I'm going to add and subtract the cost on the joint. Okay, so here all I did was I introduced the joint distribution and I subtracted it off. So what do I have now? I have the difference between the product and product right here. And I have the thing that I have a handle of by solving the optimization problem. But how do I optimize? Well, here's one option. This is the optimization problem I set up to solve, And since it's a relaxation, it's upper bounded by op plus epsilon times the parameter distances. The average of the parameter. This is just a discretization there. So I'm solving the discretized version of the problem. I know that this is going to be bounded by op plus this. Okay, so what do I do about this then? Well, I really like to use this guarantee over here, which bounds the dp distance between the joint distribution and the product. Well, the thing here is not really this. So how will I apply the dp? The key observation here is that dv is we can think of dp distance as bounding against bounded test functions. So L infinity bounded test functions give you an upper bound on total variation. So what can I do here? I can just take an L infinity bound on both steps and reduce it to the dv here. So what that do? Since we discretize these variables, we know that they lie in this bounded space. They take values that are at most 2 or and the remaining thing is just this average dp distance between the joint distribution and the product. Okay, so now we can apply this TRS kind of guarantee on this and what you get is that it brings us to condition it on 2 to the v over epsilon. That was super rushed, but at least this is maybe this gives you a sketch of how you get this doubling exponential algorithm if you analyze correlation rounding without doing anything. Okay, so this is just using this. Any questions? Okay, so let me tell you how to modify this analysis to get a win. The first question that you should ask is that the only place I truly lost was using this L infinity bound on these parameters minus dependent. It's bounding this difference by maximum support size to rest specific. Like, should I always be paying this error or can I do better? So here's an illustrative example that shows that at least initially, you cannot do better. So consider the following distribution over the optimum. You have one optimum. And you independently update each xi by adding a random sign times 2. Okay, so it's a distribution over optimal solutions. If you like pictures, here's what this is doing. It starts out with some optimal solution of line. This is 3 point in line. And what this update does is for the following distribution, this distribution shifts everything around. in expectation, you can back this about. But if you just look at the distribution, it kind of looks like it's basically it's like the sort of distances quite a lot. So if I look at the bottom distribution under this distribution, then it's not hard to show that the periodic distances are actually complete curve. Like you've lost all information, your embedding distances at essentially the endpoints of the line. So how would you fix something like this? Well, here's how you fix it. The key insight is that if I condition on one point from the actual distribution, then this essentially anchors the space of distributions into a ball of radius, which is like average distance around the root. So this way I can shift and make it the original. And if I condition on just one point, I get rid of this example where I'm taking the points and embedding them at the Let me give you a proof sketch. It's not that hard to show this sort of statement and conditioning on one point anchored this solution space. Let's say a condition on 0.58. Then I just apply Sherali-Adams and show that the probability at least 0.99, any other embedding point actually lies in the ball of this series around the 0.9. So how should you think of this radius? Well, you can think of it as being small at first. And the way to prove this is to relate it back to the objective. Okay, so I want to analyze what this radius looks like on. What am I going to do? I'm going to introduce these PIAs at me. And then I'm just going to use triangle and polar. And this first step. And this first step is bounded by the sum of the average by distances, and so is the second. So it's a straightforward computation that says that if I condition on a single point, my embedding is completely contained, at least with constant probability, in a wall of this radius along the point around the point that I conditioned. So I can no longer take this distribution and make it map points to differences. Okay, I believe that was a bit rushed, but if you have questions, I'd be happy to.
Yeah, can you say like this last computation?
Yeah.
How did you affect the idea?
Well, this is an equality. I'm adding the idea that's the question.
Oh, sorry, so I don't understand the notation there. Okay, so it's plus DIA minus A, okay, fine.
And the next thing I did was just over the square. This guy should that is. And now this guy is the objective function, right? I just reduced it all. And you know the objective function never larger than this. Like this is the trivial one. Yes, everything is yes. So then I pay 4 times the parameter. So essentially what this is saying is that if I condition on a single point, already I've like pulled out these bad examples where the distribution is doing like shifting the bad weirdly arbitrary. Okay. So how do you finish the analysis from something like this? Let me give you a sketch. Let's say this statement happens with probability 1. Okay? We don't know how to show this, it happens with constant probability, we'll deal with it later. Let's say this happens with probability 1. I'm going to do the same analysis that I did earlier. Where I go from the bottom distribution to the top distribution and look at the difference. Now, instead of using the specific bound of the maximum value that these numbers contain, I'm going to use this diagram, which is the average distance. Okay. And then I still have this T. Okay, so now what? Well, I can just apply correlation running analysis on this and make this scale at epsilon if I condition on polycave or epsilon. And now the leading tab is no longer the largest possible value, it's actually the right scaling. Okay. So this doesn't get you all the way to a polytype algorithm, this is still like exponential in the complexity. To get to all that outcome, you have to be a bit clever about your decision. So here, very quickly, the thing is that the support of the set that these yi's lie in is still exponential.
So this step is like saying that, you should think of your scale as really some kind of average as opposed to one. It's in some sense like some kind of a nice sanity check. You should not be paying in the max assumed distance, you should be paying in like the average distance of your distances. Okay.
And you're still being exponential in the big complexity because your support test is still growing. It's like from epsilon to. Okay. And you can show how to avoid this by just using.
Why don't you just replicate like you take this inside?
Yeah, you can. That's. So, what are the remaining challenges, which I don't have time to go over? The first one is that the statement that I showed you does not hold the probability one. It's just like a bound on the second one. And that you only account. So how do you account for this? Well, what we do is we analyze the tail of the embedding and show that. And the key ingredient in analyzing this is we construct some new potential functions that do not actually mirror the vertical correlation analysis. That help analyze this one separately and this. See the paper border. Okay, and the second one is that the sample size is still large. So like the YYs, I discretize them to be in a set of size 2 to the B orders. Okay. And this gives you an exponential and theta. But you don't have to discretize at this fine grade resolution. You can just consider geometrically increasing level sets of this. And that makes the support size bigger. And there's this final ingredient where you, instead of paying n to the poly k or epsilon, you can pay a constant in n. And we do this by using this solver vector. Okay, so let me end with some takeaways and future predictions. The first takeaway is that Biot's distortion is actually a poor yardstick for comparing performance of low dimensional plane. You should write projective functions instead and try to compete with like design approximation algorithms. The second takeaway is that correlation rounding in low dimensions works much better than you would expect. If you did the naive analysis, you get this doubly exponential dependence on the complexity, but you can show that at least for some problems in this routine, you can make it polynomial using the structural model. The third one, at least to me, is that complex hierarchies are key tool for analyzing the metric metric algorithms, where you write down the objective and try to compete with them. And as I said earlier, this has led to improved algorithms for the problem that I described today, also for other problems like metric multi-dimensional scaling and LP representation. And this appears as so the most natural question coming out of this work is if you actually get this PTAS, which was hinted at by Dhamdhere already in 2004, for any of these problems. Can you get a PTAS for all of them? And I'm optimistic, but I mean, when you say PTAS, this is a multiplicative question. 1 plus epsilon. But K is a constant. As in you're plotting like K to the point K or whatever. It's actually a case. Yeah, do it for K equals 1. Well, I would work. You can ask like, what kind of objective functions can this framework that we have already address? And it turns out that I don't really know how to extend it to problems like DC or stretch function. Where if you look at the objective, at least superficially, it seems very similar to the objective that I showed you. But there's some subtle differences that make our techniques like completely fail starting out. You don't know how to start. So I'm very interested in trying to understand why that is the case and then how would you expand this? Okay, like this. All right, that's it. Thank you. Right, so one thing to know is that this example, you gotta have the rate of variance. If you consider any natural function. Why, it can make. Ah, okay. Right, so all this are zero. Yeah, so if you decide like one way approximation, this probably go. Yeah. Yeah, but this particular instance is easy, you should be able to. So I think this is like the right insight for other problems too, because if you look at this other that I presented, it's just doing it like an LP image. This LP hierarchy doesn't capture any cycle. And it seems like with instance that you're just capturing the cycle. So you have like some candidate outline that we're trying, like you have but that is the right idea, you have to use it.
The people replace this dependence of B with like log of the aspect ratio or something.
So B depends on B is like the law of vast ratio. I guess show you the systemization for what so aspect ratio.
Yeah, the log of the aspect ratio is what you are also doing. So say, could you hope to get an algorithm from the guarantees of the log of the aspect ratio? For example, let's say you could have a situation where minimum distance is large, right? And so big of is be large, but really the aspect ratio is tinier than what just the big of is.
All right, so okay, so we wrote this in the sort of complexity, but you can view the else in the class. You get log. Yeah, these are. You're finding the difference between them, that you might see. After which might seem like speed up, right? But yeah, you can make these out as log. You think B and log delta? Yeah, you can have.
No more questions for Ainesh, that's okay.